Hi everyone, my name is Hananto Wicaksono, and I am a MySQL enthusiast, a MySQL database architect, and MySQL on cloud native database enthusiast and database architect as well. And today I'm happy to have this opportunity to speak about practical approach running MySQL InnoDB cluster and MySQL InnoDB cluster set on Kubernetes. Before we discuss about MySQL InnoDB clusters on Kubernetes, I think it is better if we discuss about what is InnoDB cluster first. So InnoDB clusters is basically high availability clustering solution for MySQL that uses InnoDB storage engine. Since this is using InnoDB storage engine, then typically on production environment, we disable all storage engine except InnoDB. And it is based on shared nothing architecture, meaning that every component, infrastructure component in the InnoDB clusters nodes, they are not shared. Okay, it is not using shared storage. It is shared nothing architecture. Since this is shared nothing architecture, the data is replicated over from one node to another nodes using MySQL asynchronous replication. It is row-based replication and GTID mode equal to 1. And in order to provide cluster data consistency across InnoDB clusters nodes, InnoDB clusters using group replications. So group replication is using Paxos-based consensus protocol to coordinate membership, as well as making sure that the transactions that try to commit on one node will require consensus to happen by majority of the group replication members in the clusters. So therefore, this is a solution that guarantee a recovery upon objective equal to 0, so 0 RPO. Okay. So nodes, every nodes inside the InnoDB clusters will have a consistent state of data. So since group replication does everything, high availability, data consistencies, automatic failover, and so on, and Paxos-based consensus protocol to ensure data integrity, then what is InnoDB clusters? Many people doesn't realize the differences and similarity between InnoDB clusters and group replication. And what is InnoDB clusters if group replication does everything? So InnoDB clusters basically does nothing except to provide the InnoDB clusters metadata that enables group replications to be managed by MySQL shell. That's we can use admin API in MySQL shell to bootstrap the InnoDB clusters and eventually group replications, as well as to manage the InnoDB clusters, scaling up, scaling down InnoDB clusters, adding nodes, removing nodes, or monitor the status of InnoDB clusters using admin API. Without InnoDB clusters metadata and without MySQL shell admin API, we can actually manage group applications. We can create group application, deploy it, monitor it, but it will be very tedious because it's not one commands, but it is requiring us to executing multiple commands to manage. So it is not production ready without InnoDB cluster. The other things that InnoDB clusters metadata does is basically to enable applications to connect using MySQL routers. So MySQL routers over here will provide the stable endpoints for database that application can use MySQL connector or can use GDBC connectors, to connect to InnoDB cluster through MySQL routers. And MySQL router is only one. Okay, we can have multiple, of course, and in between application and MySQL routers, we can provide a load balancer. That's fine. But technically, application does not need to understand about InnoDB cluster topology behind because of the MySQL routers. So MySQL routers will provide the tables and database endpoint. So MySQL routers aware about the topology of the InnoDB clusters, how many nodes, where they are, and which one is primary, which one is secondary. Okay, so group replications can be deployed using single primary modes or multi-primary modes. Single primary modes meaning that in the cluster, there will be only one primary that's running read-write and multiple secondary that running read-only for read-only traffic. And MySQL routers understand that. MySQL routers also will redirect the traffics to the correct nodes and expose three ports for applications to connect. An application need to decide based on the workload, typical workload that the application have, type of workload, yeah. So MySQL routers have read-write ports where the applications, LTP application, generic LTP application can connect using TDPC connections or MySQL connector into it. And any SQL statements will be redirected to the primary. And MySQL router also has read-only port where the application actually can connect, okay, and do query only, okay, query only. Let's say the application is dashboard application or reporting applications, then it can connect to MySQL routers using read-only port, and MySQL routers will redirect that connections in load balance fashions to all secondary nodes. And then depending on routing strategy of the MySQL routers, okay, we can have like least connections, so we can use round robin and so on, depending on configuration that we do on the MySQL routers, on how MySQL router distribute the read-only connections to each of the secondary nodes. As part of 8.4, MySQL router has additional port, which is read-write split, where MySQL routers getting aware about the statements that being executed by the applications. Read-write split will split DML and DDL and the query. If DML and DDL, it will be routed to be executed in primary. But if this is just a query only statement, then it will be executed in secondary. By doing so, the application does not need to know about the database topology. So this becomes matured database clustering solutions that enables data to be redundant across MySQL clusters. And group replications require us to configure in 3 members, 5 members, 7 members, 9 members. Definitely is odd members because Paxos require majority members to be available. So we don't want to have situations where there is a network partition that split the InnoDB cluster members equally. Then that's may bring down the clusters. Okay, so yeah. This slide talks about automatic primary failovers of the InnoDB clusters, where the InnoDB cluster or group application executing it, basically, if the primary node is failing, then immediately the new primary will be promoted. I mean, will be available, yeah, by promoting one of the secondary node. How fast? Is depends on multiple factors. Okay, one factor is the consistency level that being set in the InnoDB clusters. If the consistency eventuals, okay, it won't wait for data to be loaded into the new primary. It will become a primary immediately. But if the consistency level is set as before primary failover, meaning that during the primary failover, the new primary will act as before consistency, meaning that it will require primary process completions to wait for the data, all data or backlog transactions to be committed into the storage engine. At that point in time, the applications need to wait. Okay, the routers will not route the new the read-write traffic to the new primary until it is ready, which is it is a layer of protection that the solution can give, so that it will prevent the applications to corrupt the data or reading the old data. Once the fail nodes are available, then it will be available automatically joined back to the clusters. Okay, because it supports automatic healing, and it will automatically join to the clusters as a secondary node. Okay, assuming that we are configuring this as a single primary nodes. So with 3-node InnoDB clusters, it will be able to handle 1-node failure. 5-node InnoDB cluster, it will be able to handle 2-node failure. And please bear in mind, the more InnoDB clusters node, the consensus will be more expensive because it will require more node members to say yes to the transaction, to certify the transaction before transaction can be committed into the storage engine. Therefore, if we are talking about productions deployments, we need to understand about how to configure MySQL InnoDB clusters for data consistency, stability, and performance considerations. Failure detection, self-healing is easy to understand. Okay, and maybe we want to configure transaction size limit and then for compression, fragmentation, and so on, to make sure that the cluster to be more stable. Okay, in the, let's say, for example, in the various kind of networks bandwidth situations. Yeah. And then failover read safety is depending on the applications. Okay, most likely the most safer is to choose a consistency equal to before primary failover, so that the new primary, if it is elected, because the whole primary down, the new primary will be waiting for all the transactions in the backlogs to be committed in the storage engine first before receiving the read-write traffic. But not many understand about flow control. So flow control is actually very, very critical, especially for the customers that looking for increasing the throughputs of InnoDB clusters, because flow control is actually like protection, okay, to make sure the secondary will not fall too far behind for committing the transactions to the storage engine, from backlog to the storage engine. Okay, this is the RBO 0. Okay, so the transactions already on secondary engines and in secondary nodes, but maybe they are not committed yet. Maybe secondary node is busy, maybe secondary node is doing something else, the CPU is high CPU and memory utilization is very high. Therefore, it is not able to catching up with the cluster throughput. So the flow control will actually make sure that's not happened. So once the flow controls kick in, the transactions on the primary will be throttled. Okay, so for high availability InnoDB clusters, okay, then maybe we can relax the flow controls, okay, to make sure that the flow controls will not slow down the InnoDB cluster performance. Best, we need to fine tune. Okay, we cannot get the same database throughput performance between on the InnoDB clusters compared to standalone, because standalone does not have like consensus, does not have quorum process and so on. But at least we can have like best configuration for the flow controls in order to meet production throughput requirements. So I also wrote in this slides about read consistency level. There is eventual, there is before, there is after, before and after, before and primary failover, and it can be set on the session level depending on the application requirement. Okay, maybe we can set if the application is connected to secondary node, and on session level we set to before, and we run a query. Do not surprise if the query is taking longer, because maybe the data that being queried is still on the backlog transaction, because before we'll wait the new data to commit first. But again, it is depending on the customers and applications workload requirement. If no requirement of getting the new data, but performance is more important, then set it as eventual on session level. This slide talk about InnoDB clusters admin API, where we can use admin API to bootstrap the clusters. We can use admin API to add nodes, remove nodes, or maintain the cluster status. To use admin API, we need to log into the database, InnoDB clusters nodes, using MySQL shell. Okay, we log in using username, password, and then the host name, port, whatsoever, and then change the mode to JS, okay, JavaScript or Python. If the mode is SQL, because SQL mode in MySQL shell does not support admin API, only JS and yeah, Python. So once we log in, we can run command, the admin API command, and then there will be some dialogues, okay, to key in the parameter. So this causing problem, maybe questions, okay, how this solution can fit on cloud native requirement, where cloud native require automation, does not require, I mean, we need to get rid on the interactive process, but this one is more like, a lot of interactive process over here. But don't worry, because the admin API actually have one-liner admin API. So one-liner admin API is actually API that admin API that execute as one line and complete it in one line. So we can, suppress all those dialogues and so on using no wizard. Okay, so this is non-interactive mode. And we put all the parameter inside. Okay, so let's say as you see on the screen, configure instance, create clusters, add nodes, and then setting up cluster parameter and monitoring cluster status is one line, like bash commands in Linux. So by looking at this, then we know that InnoDB cluster creations can be done on cloud native fashions, okay, which is can be executed using kubectls or can be executed using CI/CDs, okay, automatically. So we are talking about Kubernetes right now. So before we jump into executing admin API on Kubernetes. So since MySQL database is stateful application, database anyway, stateful application because database require data to be persisted on the storage, then Kubernetes need to allocate the PV and PVC. Then the best way is to deploy this using stateful set because it's easy to club between the containers and the PV and PCC and so on, right? Then we need to have, let's say, a secret, okay, just to store the root password. So secret is like a key value store to store the root password of the MySQL once we want to spin the MySQL to run on Kubernetes. And then config map, if we want to have like additional system variables to be set up for our new MySQL. And then based on our understanding on workload requirement on database IOPS, we can assign the storage class, okay, to the stateful set, our stateful set. And then we also need to check about node selector scheduling and then the PDB, POD, pod disturbs budget in order for us to make sure that Kubernetes orchestrations might not jeopardize the MySQL InnoDB cluster high availability requirements, like say not jeopardizing the query, I mean the quorum process, and not jeopardizing the high availability by running multiple InnoDB clusters nodes, pods, in one Kubernetes worker node. Okay, so we need to avoid that. So we need to configure node selectors and then pod anti-affinity very, very carefully if we want to create a serious deployments of the MySQL InnoDB clusters for our productions. And then as you see, the stateful set, okay, it has 3 pods, okay, 3 containers, and then each containers will have its own PV and PVC because this is shared nothing architecture, right? So there is no PV and PVC being shared across a container. Yeah, we are talking about admin API before. And now I show you how to run admin API in Kubernetes. Okay, so in Kubernetes, we need to run my admin API using MySQL shell under kubectl. The kubectl will allow us to log into the container, okay, of the pod. Then we can execute MySQL shell over there because the MySQL container already built in with MySQL shell. So in order to deploy InnoDB cluster, okay, we need to make InnoDB clusters nodes later on able to communicate each other between containers. And this can be done easily on the VM and bare metal deployment because we can rely on IP address. We can set up the host files to configure the IP address and the host name of InnoDB clusters, and then done. But in Kubernetes, the IP address is dynamic. We cannot rely on IP address. Okay, so we need to rely on FQDN. Okay, in order for InnoDB clusters to rely on FQDN, we need to set a group replication local address to use local FQDN of that container. In order for that to happen, we need to, before we configure the InnoDB clusters, we need to set up the report host first. Okay, so we need to set the report host as FQDN of that pod. And then we need to do it in every part of the stateful set. As you see on the screen, that's prerequisite. Set process only, because the report host is not dynamic variable. It cannot be set up dynamically. So we need to use set process only, meaning that this system variable will be kept into the auto.cnf, okay, on the disk. All right, and then we need to reboot after that to make the report host take effect. But do not reboot first at this point because we still need to do the configure instance first. And then we can use kubectl to log into the pod, each pod one by one. But in the slide, it's only MySQL 2, but actually we need to do it in MySQL 0, MySQL 1, and MySQL 2. And then after that, using MySQL shell, no wizard, okay, no wizard, okay, no interactive mode. And then we use same command as if we are using that for deploying InnoDB clusters on VM and bare metal. And then after configure instance done, then we need to delete the pod. Delete the pod is not deleting the database. Delete the pod is to restart the database in Kubernetes, right? Because that's the way how Kubernetes do. If you delete a pod, then Kubernetes will try to starting up the pod again, right? Meaning that MySQL will be restarted. Since we are using stateful set, then the pod identity will be the same. Okay, so if we use replica set, then definitely it's not the same server anymore. But since we are using stateful set, we have same identity. Okay, once the pod rebooted, it will start with the same identity. Then we can use the MySQL shell admin API to create clusters and add clusters as using kubectl as if we are doing it on VM and bare metal, as you see on the screen. Okay, we just cut kubectl -n blah 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 and focus on MySQL shell, and you can find that hey, it is the same as we are setting up that on VM and bare metal. So this is how it goes. Okay, this is the result. Okay, if you are using kubectl to log in to one of the InnoDB clusters node, and then use MySQL shell and then cluster status, and we can get the same status view that we usually see on VM and bare metal pertaining to InnoDB clusters status. And on the right-hand side is the architecture. Okay, we have three nodes, three pods, stateful set. Okay, and then each of the pods will contain one container, which is a MySQL container. Okay, and then each containers will have attached pod or PV and PVC attached into it. And then they are communicating each other using FQDNs because we have SVC on top, the headless services that ensure that MySQL 0, 1, and 2 can communicate each other using FQDN. All right. Then this is MySQL routers. We are discussing about InnoDB clusters just now. Now we are discussing about MySQL routers deployment on Kubernetes. So MySQL routers on Kubernetes, since we know that MySQL routers does not process data, is actually a stateless application, then we can deploy MySQL routers not using stateful set. So stateful set is just an option, but we can deploy MySQL routers using replica set or using deployment or using daemon set, okay, on Kubernetes. And I wrote a blog quite some time ago, how to run MySQL routers on Kubernetes manually. And it is suitable for MySQL routers that connects to InnoDB cluster that are running outside the Kubernetes. Also, it can be same concept also can be used for connecting to InnoDB cluster that are running inside the Kubernetes. And if it is running outside the Kubernetes, then of course we need to create endpoint for each of InnoDB cluster's nodes, so that the MySQL router traffic can reach the InnoDB cluster database that running outside the Kubernetes. I also wrote MySQL router operator using copf. Yeah, this is my own MySQL routers operators to deploy MySQL routers on Kubernetes for InnoDB clusters that running outside Kubernetes or inside Kubernetes. Then you can check on my GitHub, https github.com/AAA-SG MySQL routers operator, or you can check on my blog, okay, for MySQL routers operator on Kubernetes with Python copf. How about MySQL operators by Oracle MySQL? Well, deploying MySQL InnoDB clusters using MySQL operators by Oracle MySQL is very, very easy and straightforward. Okay, once we understand about how to do deploying InnoDB clusters manually on Kubernetes, then understanding how operators works, okay, what this operator can give, okay, for the InnoDB cluster deployment on Kubernetes, it becomes easy for us, become very, very clear. Okay, first of all, we need to install MySQL operator. We can install using kubectl plus manifest, or we can use Helm, as you see on the screen. And then next, we can create a secret. We can also, then we can create the manifest for InnoDB clusters deployment using MySQL operator. As you see over there, there is kind InnoDB clusters. What is that? That means MySQL operators add more CRD, custom resource definitions, related to MySQL InnoDB clusters on Kubernetes so that we can call in manifest. All right. And then we can set up instances for InnoDB cluster. Three meanings that there are 3 pods, one stateful set, 3 pods, and it will automatically set up as InnoDB cluster, 3 node InnoDB clusters. And routers is 1 instance, 1 replica set, 1 instance MySQL routers. Very easy compared to the manual one. And you won't see any difference between manual and using operator. Okay. In terms of MySQL shells, cluster status, they are the same, right? Same. However, from the Kubernetes standpoint, there are slightly differences between manuals and the operators. The operators will have 2 containers per pods. One container is for MySQL container, and the other container is for sidecar containers, where the operator works to monitors, to do some automations that typically cannot be done when we deploy on manual. Let's say, for example, the whole entire Kubernetes down, and when we start, and we need to do reboot cluster on complete outage on the InnoDB clusters. That can be done using the sidecar containers, the MySQL operator agents. Okay, but on manuals, we need to use CI/CDs, or we can use, we need to log in manually using kubectl and execute commands, reboot cluster on complete outage. All right. Then why I need to use manuals? Why I need to use operators? Why I need to use a manual with CI/CDs? So manual deployment actually very so-called fun, yeah, very exciting. Okay, because manual deployment will help us. Okay, it helps to expose and understand the moving parts, while MySQL operators will be kind of like give us standardizations and automations much of the life cycles. In InnoDB clusters on Kubernetes, the InnoDB cluster responsible for the entire high availability of MySQL. The data integration, data integrities, data consistency across clusters is, and failovers on primary failover is not done by Kubernetes. It is done by kube replication inside the InnoDB cluster. The Kubernetes is providing the automation on infrastructure level, but that's why we need to check on some of the Kubernetes configurations, okay, so that it won't jeopardize the quorum process of the InnoDB clusters. Okay, for example, by doing the anti-affinity, for example, to make sure that the pods on the same InnoDB cluster will not run on the same Kubernetes worker nodes. But MySQL operators will give like automation and orchestrations. Okay, it gives definitions of the InnoDB clusters as custom resource definitions on the Kubernetes. Cluster bootstrap is automatic. MySQL router is also automatic. Operational risk is also lower than manual Kubernetes, manual deployments of InnoDB clusters on Kubernetes. But we can create Groovy script, and then we can use CI/CD like Jenkins to run that Groovy scripts to run standardized scripts to deploy DB clusters on Kubernetes manually. That also can be done. I had one project last time once to deploy on top of OpenShift. Since MySQL operator does not support OpenShift anyway, so we need to deploy on manual. Okay, and I use a Groovy script basically to automate the deployment as if it is running on MySQL operators, using MySQL operators. And manual deployment will provide better flexibility compared to the operator one, because manual deployment will be able, like say, for example, tackle some situation if the requirement is to deploy InnoDB clusters, three node InnoDB cluster across three Kubernetes clusters. That cannot be done using MySQL operators, because MySQL operator is only able to manage resources that belong on the same control plane. Okay, cross control plane cannot be used. So, but that can be done using manual kubectl deployment. Again, this is just to emphasize what we have discussed before. For production grid setting for MySQL on Kubernetes, check the storage class, check the node selector, check port affinity, topology, spread constraints, port description, budget. Make sure that it has CPU and memory without, overuse, and then liveness probe, radius probes, network policy, taints and toleration, and so on. That's very important if we are going to deploy MySQL InnoDB clusters seriously on the production environment. So how about the InnoDB cluster set? What is InnoDB cluster set all about? So InnoDB cluster set is DR-ready InnoDB clusters, okay, by creating multi-InnoDB cluster and use asynchronous replication to replicate from the primary cluster into the replica cluster. So we are talking about more than one InnoDB cluster. Can be two, can be three, but primary cluster is always one. So the primary clusters of the primary node of primary cluster is the only nodes within InnoDB cluster set that works as read-write. The rest of the primary nodes on the replica cluster is always running on read only, and this is kind of like orchestrated. It is very nice. Okay, very integrated solutions. I love this InnoDB cluster set. I think this is kind of like a mature solution for providing the disaster recovery ready for InnoDB clusters. Okay, without heavily require good bandwidth connectivity between two data center, right? It's because the data from the primary cluster to replica clusters done through asynchronous replications, okay, GTID controls and role-based replication. But how about with Kubernetes? Okay, so how to deploy a MySQL cluster set on Kubernetes? Usually, MySQL cluster set on Kubernetes deployed on different Kubernetes cluster. Okay, a separate Kubernetes cluster, separate control plane. Therefore, MySQL operators will need to be installed on each Kubernetes cluster. Okay, and we need to provide networking, okay, to be available on the Kubernetes levels to club these two Kubernetes together. Okay, usually we can use like, solution like Cilium, Calico, Submariners, or even Scupa. And I wrote blogs when I was in Oracle blogs To deploy MySQL InnoDB cluster set across Kubernetes clusters using Cilium, I wrote detailed commands and step-by-step of to deploy InnoDB cluster set manually on Kubernetes, on 2 Kubernetes clusters. And Cilium, Calico, and Submariners will provide layer 4 networks communications between two Kubernetes cluster. Therefore, InnoDB cluster that running on one side can communicate to the other side, but not using IP. Okay, more using FQDN. Okay, but it's strongly advised that both clusters, okay, should use the different CIDR blocks. Okay, and this is the Cilium setting. Okay, taken from my blogs. First, we need to ensure that production Cilium and DR Ciliums can able to production Cilium and disaster recovery Cilium can able to communicate each other, right? And then since it is based on FQDN communication, then we need to make sure that FQDN is recognized by DNS. So we need to pass the DNS on a production. That's if the traffic is going into the disaster recovery through FQDN, the production will understand the Kubernetes in the production will understand. Vice versa, we need to patch the core DNS in disaster recovery Kubernetes cluster as well, so that it can understand to actually send the traffic across Kubernetes cluster. Then after that, once the network is done in Kubernetes level, then the rest are just MySQL. Okay, so we can configure InnoDB cluster set on production Kubernetes cluster. Okay, using kubectl and then create cluster set and then followed by cluster set name. Then there will be a change on metadata. The routers will need to be rebooted again, okay, to take this new metadata. So that's why we need to roll out and restart deployment of the MySQL routers. And once done, okay, we already have InnoDB cluster set running on production with one cluster in Kubernetes cluster, production Kubernetes cluster, and routers already set up as well. Next, we need to add InnoDB clusters on disaster recovery Kubernetes clusters into the cluster set. So to add a replica cluster to a cluster set, we need to dissolve first InnoDB clusters on disaster recovery. And then we pick up one pod, okay, and we add that as the primary nodes of the replica cluster and join that as the new InnoDB cluster. Okay, the new InnoDB cluster, which is the replica cluster. Okay, as you see over here, create replica cluster, and then we can show status, cluster set status to see. Now we already have 2 clusters, which is cluster that running on Kubernetes production and cluster that running on Kubernetes disaster recovery. Okay, Kubernetes production using 3 nodes and Kubernetes disaster recovery only 1 node. Right now, still 1 node. Then after that, since productions and disaster recovery may have a different password, okay, cluster admin password. Then we need to sync the cluster admin password. Then we need to export InnoDB cluster admin password, okay, secret, yeah, export the secret and import this secret into the Kubernetes in disaster recovery. Once it is imported, then we can safely add node 2 or node 3 on InnoDB cluster in disaster recovery Kubernetes. Okay, so we have 3 and 3. 3 InnoDB cluster on productions and 3 InnoDB cluster on DR. Okay, both are different Kubernetes clusters with different control planes. Okay, each have its own control plane. Yeah. Good news, the MySQL operators now support InnoDB cluster set across Kubernetes cluster. You can check in Oracle blocks. Yeah. And then since MySQL operator cannot manage resource across InnoDB cluster, I mean across Kubernetes cluster, okay, because it needs to have same control plane, then each of Kubernetes clusters need to have different MySQL operators. Okay, and Cilium's, like I show you, provides a low-level networking. Okay, and we need to avoid overlapping side range. Okay, and then maybe we need to patch the core DNS. Okay, so that's the Kubernetes we understands to forward the DRFQDN into the Kubernetes clusters in disaster recovery and vice versa. And Submarine also, it provides connectivity similar to Cilium, but more simple and lightweight. All right, I covers InnoDB clusters on Kubernetes manual way, InnoDB clusters on Kubernetes using the operators, InnoDB cluster set using manual, and InnoDB cluster set using operator way. Thank you so much for listening to my presentations. Thank you.